Okay, we're going to talk about more about vectors. We have seen some of these problems before, but we're going to approach them in a bit of a different way. This time we're going to look at the components of vectors. And so first, I want to define a force vector. That is a vector that represents a direction and a magnitude of an applied force. So it's just a vector that represents the magnitude and direction. Of course, it's got two dimensions to it of an applied force. Okay, and then a resultant force, or a force, I think I have these backwards. This should say resultant force. So maybe by the time I get this to you, it will be corrected on yours. It's the sum of two forces being applied to an object. So this is the sum of two forces being applied to an object. So, for instance, we can draw this a little bit. What if we have some force here, and then we have some other force here? That's this first force, okay, and then we have another one that's applying this second force here. Okay, what we did before was we did the parallelogram approach, and we found the resultant was the diagonal of this, and the resultant force was the sum of these two forces. Okay, and we used the law of cosine to be able to figure out what that particular resultant was and his direction. And that is fine, but what I'm going to show you is something that is probably more commonly used and more practical, especially if you're going into physics or any kind of engineering, and that's the components. And so when you look at this, if we take this same situation where we've got two forces being applied to an object, the sum of these two forces, what we're going to do is break each force down into its components. So if we've got this first force F1 here, let me redraw it here. It's at a bit of an angle, let's say. This is F1, okay. He has an x direction called F sub 1 x, and he has a y direction called F sub 1 y. So F1, this first vector, can be broken down into its x and y components. Okay, then F2, which is this guy right here, F2, he also has an x component and a y component that it's made up of. So F2 is comprised of F2x and F2y. Okay, now to get the resultant vector here, R, it is the sum of the x's, F1x plus F2x, the sum of the y components, F1y plus F2y. And many times in physics and engineering, it's easier to break something down into its components and simply add the x components and the y components. Now, what they will ask for is the resultant force. They want to know its magnitude. So then we would take the magnitude of R, which is the square root of, if you call this R1x, R2y, it's the x component, or I don't need to say R1 or R2, I'm sorry. Just Rx and Ry, that's because these have been added. Rx and Ry, okay. Rx squared plus Ry squared, that's its resultant. And then its angle, what angle this guy is, theta, is equal to the inverse tangent of ry over rx. Now, how do we find out what f1x and f1y are? So this is you've seen this so many times. This is it is the trig functions. So if we've got, let me just pull one of these. Let's just say we got some force F at some angle. And so you can break it down into its y component. Here's our right angle, and its x component. Well, if this is theta, this is some angle theta, we know that the cosine of theta is adjacent over f. So let me just write that down. The cosine of theta is adjacent, which is f sub x over f. Okay. So if we want to solve for f sub x, that's equal to the resultant, the magnitude of the resultant. So I have this vector. I should really say magnitude, not resultant right here. Sorry. Of f times the cosine of theta. And similarly, the sine of theta is opposite over hypotenuse. And so we could solve that and say, well, what is f sub y? It's going to be f times the sine of theta. So at first glance, it looks like we're doing way too much work. Like, why in the world would we do all this? It really becomes simpler once you start getting into it. So let's just get into it. Let's do the first example. And so it says a powerboat is traveling at 35 kilometers per hour. It has a compass heading of 85 degrees. This is called its apparent velocity. Okay, so you've got some water here, some water. Okay, you've got a boat that, if this is 90, perpendicular is 90, 85 is going to be like something like that. Okay, he's traveling at 35 kilometers per hour, and this is called the boat's apparent velocity. All right, so but there's a strong current, and the current is headed 22 degrees. So if you think of the horizontal, 22 degrees would be about like that. So we're going to go about like that. We're going to add this second force on here. This is our current. And so the actual speed of the boat is going to be the sum of these two forces. So this is the resultant right here. Okay, it is the sum of the apparent velocity. The boat is headed off in this direction, right? But there's another force besides just the boat's power that's acting on it, which is the current. It's pushing it that way. And so the purple is the resultant. Okay, so how we're going to find the resultant force is we're going to add the components of the boat vector. So if I call this the boat vector, okay, and so against the horizontal, this is 85 degrees. So this is my boat vector. And so this is the x component of the boat vector, and this is the y component of the boat vector. It's made up of these two guys. Here's my right angle. So right here, this is going to be my x component. This is going to be my y component. And this is going to be, together that makes up the boat vector. Okay, then, in addition, we have the current vector right here. So if this is a horizontal, the current vector is like at 22 degrees. This will represent it. And so this will be the current. This is the x direction for the current, and this is the y direction for the current. And so his resultant, or the current, is made up of his x component and his y component. Okay, now to get the resultant vector, the r, for this, which incidentally is called the actual velocity. This is the actual velocity. Okay. We're simply going to add the boat x plus the current x. And then we're going to add the boat y plus the current y. And that's going to be our resultant vector. Okay, so we're about to do that. Now, what was the angle of the boat? It was headed at, this angle in here is 85 degrees. What was the angle of the current? This was 22 degrees. All right, we're basing this off of, these are the big, f sub x in general is the resultant magnitude times the cosine of theta. F sub y is the resultant magnitude times the sine of theta. So we're going to use that. B sub x will be, the boat is headed out at 35 kilometers per hour. And so this is a typo. I hope I fixed this as well before you guys get your sheet. That's kilometers per hour. The boat is 35, okay, and the current is 8. All right, B sub x is 35 times the cosine of 85 degrees. B sub y is 35 times the sine of 85 degrees. Similarly, C sub x is going to be the magnitude 8 times the cosine of 22 degrees. And C sub y is going to be the magnitude 8 times the sine of 22 degrees. I'm going to get my calculator out, and I'm going to make sure my calculator's in degree mode, and I'm going to get a value out here for B sub x. Ends up being about 3.05. B sub y ends up being 34.9. C sub x ends up being about 7.4. And C sub y ends up being about 3. All right, so I'm going to add B sub x plus C sub x to get my x component of the resultant vector, and that ends up being 10.5. And then if I add the y components, I get 37.9. Okay, so this is my resultant vector, r, or the actual velocity. What we want is its magnitude, and so we're going to do that just by taking the magnitude of this, which is the square root of 10.5 squared plus 37.9 squared. And what we get there is that it's about 39. And so this means 39 kilometers per hour. That's his actual speed. And then what direction is he really headed? We got to figure out theta. Theta is the tangent inverse of the y component, 37.9, over the x component, 10.5. And that gives us, I got for that, let me just see, I got 74.5 degrees. 74.5 degrees. So if we had to write a sentence, I've run out of a lot of room. If it said find the actual speed and direction of the boat, you could say that the actual speed of the boat is 39 kilometers per hour, headed at, with the compass heading of 74.5 degrees. That is its actual speed and direction. Okay, so that's an example of how you can do that. We're going to look at a few more examples. Let's go ahead and do number 2 right here. This is one I know that we did using the law of cosines. But now we're going to look at it with components of vectors. So it says, I just think this is the most hilarious picture because it's so dated, but it's funny. You get the point. There's a man and his horse, and they're both pulling on a piece of granite, as shown in the figure. The angle between the force vector of the horse, so the horse is pulling this way, is, and the man is pulling this way. The angle between these guys is 45 degrees, okay? So, if the horse is pulling with the force of 800 pounds, and the man is pulling with the force of 200 pounds, what is the magnitude and direction of the resultant force? So in this example, we have two forces, and we've got the horse, and we've got the man, right? So what I'm going to do here is, vectors are in space, and we can orient them the way we need to orient them, however we'd like to. So what I'm going to do with this one which I'm going to handle this one just a little bit differently. I have this force here, right, and this one here. Now this may be at some angle, but I'm going to choose to make my horse vector parallel to the horizontal. I'm going to make it just along the x-axis. So this is 800 pounds. Okay, and then my the man is pulling that way. This is the horse vector. The man's vector, so this is the vector, okay. The man is headed up this way. This is the man. He can't pull as strong, so he's got the length is shorter, 200 pounds. Well, that's going to be in my way. I got to move this. 200 pounds is going to be this way. Okay. Now, they gave me the angle between these, but by choosing the horse vector to be parallel with the horizontal x-axis, I know that the man's angle, the angle with which he's pulling, is going to be the angle between the forces. So this is 45 degrees. That makes that very simple. This is going to be called m sub x. This is m sub y. Here's my x direction for the man, my y direction for the man. So when we do this, look at the horse's vector. He has no y component to him at all. It's 0. He only has an x component to him. So that makes it pretty simple. If you want to think about this in terms of angles, what angle would this be? This would be the angle 0. So I'm going to do this very technically with the angle and everything when we calculate h sub x. H sub x is the magnitude, which is 800, times the cosine of the angle. I don't even see a triangle. The angle is 0 degrees. Let's think about that. That's 800. What's the cosine of 0 if you think your unit circle here? Here's 0. The cosine is 1, and the sine is 0. So 800 times 1 is just 800. In other words, the entire force is being pulled in the x direction. H sub y is 800 times the cosine of the angle 0. Sorry, not cosine. The sine of the angle 0. And what is the sine of 0? Well, it is 0, right? So this is 800 times 0, which gives you 0. And this matches our picture. No force is being exerted in the y direction. So h sub x in this is 800. H sub y is 0. All right, great. Let's do m sub x. M sub x is going to be the force which the man can pull 200 pounds. 200 times the cosine of 45 degrees. M sub y is the magnitude 200 times the sine of 45 degrees. When you put this in your calculator, you'll find that m sub x is about 141.4, and so is m sub y, 141.4. This should make sense because it's at 45 degrees where the sine and the cosine are equivalent. Okay, the resultant force of these two guys acting on each other. What is the resultant of the horse and the man pulling? I'm drawing it just a little bit different than the picture because I'm doing the addition of forces in the head to tail method. So let's see. If this is the horse pulling, and then the man's pulling with whatever he can offer, the resultant vector is this right here. So this is what we're really after, and we want to know what angle the granite's being pulled with respect to the horse's force direction. So let's proceed. The resultant is going to be the sum of the x's. So m sub x, 141.4, plus h sub x, 800, gives you 941.4. M sub y, 141.4 plus 0. H sub y is going to be 141.4. We are going to find the magnitude of r, which is the square root of 941.1 squared plus 141.1.4 squared. And when you do that, you find that the magnitude of this is going to be 952 pounds. Okay, and the angle is the tangent inverse of 141.1 41.4 over 941.4. And this gives us an angle of 8.5 degrees. 8.5 degrees. So, that is the direction it's moving with respect to the horse. Okay, let me just pause so that the video doesn't get too long.